We're back. Can you hear me okay this time? Amazing. All right. So, talking about types of selection that can occur in a population, first we need to talk about our baseline and what we're starting with. So on our y-axis, we're going to have relative abundance or number of individuals. And then on the x-axis, we're going to have the trait with a greater expression, like the greater extreme at the positive end of that x-axis and less of the trait on the lower negative x-axis, closer to 0. So in all of these, we're going to have, I'm going to draw our normal distribution as kind of a reference point and then draw the type of selection in red. So this would be our normal. And normal in this case is in the statistical sense. For this first one, let's say that we have a selective pressure that favors one extreme, the more extreme expression of this trait. So we have movement in one direction. And I keep repeating this word because that is called directional selection. Same but different. If we have a selective pressure that punishes extremes at either end, over generations you're going to have a greater concentration of individuals with that intermediate trait, and this is called stabilizing selection. And finally, you have the inverse of this, where the intermediate for a trait is punished by whatever selective pressure exists, and the extremes at either end will be favored. So you'll have something that looks more like this. And this is called disruptive selection. So directional favors one extreme, stabilizing favors the intermediate, and disruptive favors extremes at either end. So now we examine the scenarios in the following pages, and for each scenario we have a couple of things we need to answer. First, decide whether or not natural selection is operating. And to do this, in doing this, indicate whether there is variability in the populations. If no, what does this imply about evolution? And if yes, what is the nature of the variation? For example, what characteristics must be the variation? What characteristics must the variation have for selection to operate on it? There isn't actually a question here, that's just a placeholder. B, is there any indication that members of the populations differ in fitness? And if no, what does this imply about the operation of natural selection? If yes, describe the difference in fitness. And C, given the answers for part A and B, what trend should characterize the future behavior or composition of the populations? So again, is natural selection occurring? Is there a difference in fitness? And what trends will we see in future generations? So in our first scenario, a particular species of mouse feeds on the seeds of a single species of cherry tree. So we already have two organisms. We have mice and cherry trees. When the mice eat a seed, they digest it completely. This is going to be important. They digest it completely. The mice choose seeds of intermediate and large sizes, leaving the very small seeds of the cherry tree uneaten. Graph the abundance of the different sizes of cherry tree seeds over 10 seasons and explain your rationale for drawing your graph this way. So the question is asking us about seed size. So all of our filters right now, the mice are the selective pressure and the seed size is the trait. Let's see. Seed size is the trait that is being selected for or against. So if we have, the mice choose seeds of intermediate and large size, leaving the very small seeds of the cherry tree uneaten. So throughout the lifespan of the organism. We're assuming the tree makes seeds of all different sizes. If seed size is a heritable trait, then we should see over many seasons more small trees, or small seeds rather, in the trees. And we're assuming we started with kind of the same amount. We should see a relative downward trend. Maybe I could make that a little clearer of a downward trend of the medium and large size seeds. And going back, let's see. So I kind of skipped to the end there, but A, is natural selection occurring? Yes. B, is there a difference in fitness? Yes. Small seeds escape predation and reproduce. And C, future generations of these cherry trees will produce relatively more small seeds. And again, our chart should show that over time, actually, I have inappropriately labeled our chart here, so I'm going to make an amendment. This is time over many seasons. We have our 10 seasons. It doesn't really matter, but we still have relative abundance on the y-axis. So far, so good? Because we're about to mix it up. Small island A. Where am I? Contains 3 separate populations of a single species of cherry tree. The seed size varies between trees. That is, some trees produce seeds that are all in the small size ranges, others produce seeds in the middle size ranges, and others produce seeds in the large size ranges. A small population of mice is introduced to the island. So these are not native. The mice eat cherries that are the mice eat cherries and are the only predators on the cherry trees. When the mice eat a cherry, they completely digest it and the pit or seed inside it. The mice choose medium and large seeds and leave the smallest seeds uneaten. So this is very much the same situation as the previous prompt, but what we've changed here is that one tree produces one size of seed, rather than having many sizes of seed within a tree. But the selective pressure is still very much the same. So A, is selection occurring? Yes. Mice eat medium and large seeds, so small seeds favored. B, is there a difference in fitness? Answer is yes. Individual seeds differ in fitness. Small seeds more fit. Fitness meaning goes on an increased likelihood that they will go on to reproduce and produce more offspring and carry on their genetic material. We're not talking fitness like going to the gym, right? It's very, very different. So yeah, mice are selecting against the very large and the medium seeds. Only the small seeds are not eaten, and therefore many more small seeds will be left relative to the other sizes to produce the next generation of cherry trees. What trend are we going to see long term if this selection occurs long term? Future generations, of course, of cherry trees will produce more small seeds, or we will see more small seeded trees. Future gens will be made up of a greater proportion of small seeded trees. Graph their abundance. This chart is going to look very much the same. Again, we have time on the x-axis and relative abundance on the y-axis. At the time that the mice are introduced, small seeds are going to start doing really, really well relative to medium and large, which are going to decline and may eventually die out. All right. Next scenario. Would your answer for the previous scenario change given the following information and explain? As you continue to study the populations of trees, you note that the viability of the seeds varies with size, such that the viability of the small seeds is less than that of the middle-sized seeds, which is less than that of the largest seeds. So in the previous prompt, middle and large-sized seeds were being eaten at a higher rate, but now we're also learning that the bigger the seed is, the more likely it is to be viable, to be fertile, to reproduce. So assuming that it survives predation, it's more likely to produce a tree versus the small ones, which aren't being eaten, but are less fertile. So how is this going to impact future generations? Is what the question is asking, but we still need to go through. So yes, selection is occurring. The trait being selected against is seed size. For selection to be operating, the assumption is that seed size is heritable. Is there a difference in relative fitness? Again, yes. Individual seeds differ in fitness. Large and medium are more viable. But small are more likely to avoid predation. So they're competing selective forces, right? So what will the makeup of our population be moving forward? And in this scenario, you really need to consider both of those competing selective forces, the effects of selection by mice and the difference in relative fitness of the seeds related to size. So as long as the mice are not eating all of the medium and large seeds, some are going to remain to reproduce and produce individuals in the next generation. And that may be sufficient to maintain relatively equal numbers with the smaller seeds that aren't being eaten but aren't as fertile, right? Aren't as viable. So in future populations, the proportion of trees producing each seed type really depends on both the numbers of large and medium seeds that survive and the small seeds that are uneaten, and the relative viability of each of these. So future makeup will really depends. Depends on impact of predation on medium and large, and relative viability of small seeds. Cool. Remember? Scenario 3. Different island. Small island B contains 3 separate populations of a single species of cherry tree. Unlike the species on island A, in this species, seed size varies within trees. Okay? That is, each tree produces seeds that range in size from large to small. A small population of mice is introduced to the island. These are the only predators on the cherry trees, and when the mice eat a cherry, they digest it and the pit or seed completely. The mice choose medium and large seeds and leave the small seeds uneaten. I may have misspoken on the first prompt, but at any rate, we should kind of see a pattern emerging here. This one, we get a little wiggle room here. Selection could be occurring if you assume that seed size is a heritable trait, right? If each flower on a tree is independently pollinated to produce its seeds, then the individual seeds on a tree can have different combinations of genes. However, if you notice that the most shaded parts of a tree produce cherries with small seeds and the sunniest parts of trees produce trees with large seeds, you might reconsider your assumption, right? So selection may be occurring assuming seed size is a heritable trait and no environmental factors such as sunlight, nutrition, etc. impact seed size. So part B, is there a difference in relative fitness? Let's say seed size varies with nutrition as opposed to genetics. The selection against large and small seeds isn't necessarily selection against any particular genotype in that case, right? In that case, there would be no genetic difference in fitness. So if seed size varies with nutrition or some other environmental factor, then no relative difference in fitness based on heritable traits, but based on genetic differences in size. Or there's no genetic difference in fitness. Yeah. And finally, what are future generations going to look like? And again, if there's no selection based on heritable differences here, then the population should remain relatively stable, even though the mice prefer those medium and large seeds, right? If there's no selection and no difference in fitness among surviving seeds. Then population should remain stable. Is that difference clear to folks? Like if seed size is influenced by something other than genetics, if a small seed and a large seed both produce trees with an even number of large and small seeds, it doesn't matter that only the large seeds are being eaten because the small seeds are still going to produce offspring genetically identical to the others, right? Cool. All right. Graph the abundance of the different sizes of cherry trees over 10 seasons on Island B and explain your rationale for drawing the graph this way. I don't think we need to hammer this one too hard. Whereas before we were seeing a really big difference over time, we should see trends that kind of match each other in this case. You may see some fluctuations over time with seasonality or natural disasters, things like that, but they should stick together, right? Because seed size, again, is not a heritable trait that is, being selected against. Okay. Scenario 3. Make sure you can actually kind of see that. Would your answer for the scenario 3A change given the following information and explain? As you continue to study these populations, you note that the viability of the seeds does not vary with size. Over time, however, you find that the trees that grow from the smallest seeds produce fewer large seeds. I like this question because it has added just one little change that has reintroduced the mice as an indirect source of selective pressure, right? All seeds still produce small, medium, and large trees. All seeds still produce trees with small, medium, and large seeds. However, the small seeds produce fewer trees from small seeds produce fewer large seeds. And so we're selecting against those large seeds again because those are being preyed upon by the mice and they're getting to reproduce less often. So this provides evidence that seed size is a heritable trait. And not only the result of growth conditions or the environment, right? Therefore, selection is occurring. 2 C's. Crying out loud. And over time, we would expect the population to look very different, to have more small seeds again. Future generations will have an increased relative number of small-seeded trees. Scenario 4. After a severe spring ice storm, about half of the finches, these are a small bird, in a population are found dead. Examination of the dead birds indicate that they vary in age from young to old. About 60% of the dead are fledglings, just left the nest, and about 20% are over 3 years of age, which would be very old for this species. So, going back to our original prompts, is selection occurring? And again, for selection to be occurring here, it must be a heritable trait that is being selected against. So I would argue that this is not selection. And this is simply because the vast majority of the dead birds were very young and the very old. And it follows that any adult bird that would have survived this had to have been a fledgling at one point, right? And so that isn't really a trait that can be selected for or against in a heritable sense, right? These characteristics are not based on genetic differences in these individuals compared to the rest of the population that survived. So age is not necessarily a heritable trait being selected against. Is there a relative difference in fitness? No. If this were selection, it would be against young and old ages. And again, if we took this to extremes, we would have to argue that over time, each subsequent generation would have more middle-aged individuals compared to the number of young and old, which is just not possible, because middle-aged individuals must have been young at one time. So no selection, no difference in fitness, and without any further information indicating a trait that could be selected for or against by these storms that is heritable, we shouldn't really see a major difference in the genetic makeup of this population over time. Cool. The figure below shows the distribution of a phenotypic characteristic in a population of organisms. Phenotypic just means that it is being expressed and we can observe it. Right? The alleles for these characteristics are being expressed. They are shown in three proportions, A, B, and C. For parts A, B, and C, for the following situations, which portion of the population will be selected against and be least likely to have their genes represented in the next generation? And explain your answer. Male sticklebacks. See if we can... kind of. Male sticklebacks with bright red coloring are favored by female sticklebacks as mates. However, the bright red color makes the male more likely to be seen by predators. So in our chart here, if this is more red on the x-axis, way down here, which population is least likely to go on and reproduce? So if they are super bright red, they're going to get eaten. So it's not C. But the brighter red it is, the more likely they are to find a mate and reproduce. So presumably, if they have no coloration, they're also going to have a hard time reproducing. So this would be an example where the intermediate characteristic is favored. This is stabilizing selection. Favoring intermediate coloration. Too bright gets eaten. Too dull. No mating. On Island Z in the Galapagos, the plant population contains only 2 species. One of the 2 plant species, produces very large seeds, and the other produces small seeds. A species of seed-eating finch has lived on the island for many years. Members of this established species have large beaks and prefer large seeds. A small population of a different species of seed-eating finch has migrated to the island. The beak size in the new species population varies over a continuum from relatively small to large. How will evolution of the new finch species be affected? I'm going to go ahead and redraw our chart here. Okay. We have large seeds, we have small seeds, we have large beaks that prefer large seeds, and presumably, and then a new population of birds that has a continuum. So beak size is one of the traits that we are selecting for. We're not worried about seeds, right? In this particular case, we're interested in what will happen to the new finch species. So if the existing finches already have large beaks, they're eating all of the large seeds, the new population of finches is going to be in direct competition with them, right? So that rules out this extreme, right? But some portion of the intermediate is also going to be in competition with them because there's, as far as we know from the prompt, only small and large seeds. So C is the best answer because they're in direct competition. C is the best answer. C are least likely to reproduce because they're in direct competition with the native population. B will also be affected since they'll be in direct competition with the birds that have smaller beaks and are eating all of the smaller seeds, presumably, and in competition with the large-beaked birds eating the large seeds. This would be an example of directional selection. Favoring small-beaked birds. In a species of plant-eating land snail, the shell color is variable and ranges from very light to intermediate to very dark in color. The snails are preyed upon by birds that use sight to find their prey. A small population of these snails is moved to an island where the food plants in their preferred habitat are either very light in color or very dark. So we have very light and very dark in our substrate. And we have shell colors on these snails that are very light, intermediate, and very dark. We can safely assume that the shade, the color of these snails' shells is functioning as cryptic camouflage, right? On a dark background, the dark ones are going to be the least likely to be seen. Inversely, on a very light background, the very light-colored snails will be the least likely to be seen and eaten by predators. And this is an example where the intermediate of the trait in question, in this case the lightness or darkness of the shell, will be punished. They will get eaten. Disruptive. Disruptive selection favoring either extreme. Intermediate coloration gets punished. And so B the intermediate, are the least likely to survive and reproduce. Cool. That's all I have for you tonight. Thank you all for your patience on the front end and helping me troubleshoot the new setup. If you have any questions, feel free to email me directly. Otherwise, enjoy the rest of your week, and I will. Don't forget to turn in your worksheets for extra credit by Friday, and I will see you next week.